Welcome to our classroom. Welcome to the classroom. Welcome to the classroom. The segments where I bring the classroom out into the field to teach you about geological processes. Welcome to the classroom. Today we're here going to use this boulder to help us understand collecting and interpreting geological data in the field. I have my helpers here, 3 Lego people that are going to help take measurements at 3 different locations. And we can use these 3 points to determine the orientation of a plane in space. Now, what we would do at their scale, we'd go along and we would measure. We have foliation planes. You can see darker and lighter layering, a much darker top here. That layer comes around here, but you can see it permeating throughout the entire block. We also have quartz veins intersecting the block at different angles, so they've been intruded after the fact. They're cross-cutting the foliation plane. So let's focus on that foliation plane. We have a person here and a person here. They're at the same plane, that contrast between the light and the dark layers. So they can take a measurement at each location. Like this gentleman can't see the other helper, so they are going to take independent measurements, and we have to go back to the office, look at our Clino app, and see that everything agrees at the end of the day. But what we would do is we'd come, use our right hand or the Clino app on the phone, and take a measurement, and we would see this plane sort of dipping down in this direction. So I'll put my hand here, right hand. The plane is dipping down in this general direction. So the measurement here and on the back side here should all agree, generally speaking, within maybe 20 or 30 degrees at most for the strike, and maybe 10 or so degrees for the dip. So what we want to see is that the measurements around on this foliation plane all agree, and they will agree presumably around the bigger area. But if they don't agree, then we have to understand if we're dealing with a fold or if there is a fault or something that would disrupt the measurements. So these things can happen in the field, and we have to walk around and have a look to understand, are we dealing with a fold? But at this scale, on this outcrop, it's a planar foliation. Now, we could consider that this darker top and the lighter bottom would be 2 different rock types. And so if we can observe that contact between dark and light, then we can understand and project where that contact exists in surface. So pretend we can't get to this side of the boulder. Well, we could take 3 points, 1, 2, 3, and determine the orientation of that plane in space, just using those 3 points. And then we can project it to places we can't go or places we can't see the contact. So that's a way we can interpret the data. We have to first take the measurements in the field. We have to look at the data in the office on our stereo net using the Clino app. And then we make an interpretation about what those measurements mean. We understand that those measurements are all planar that we've taken. So then we can assume, at least from the maximum range where we've taken measurements, that that plane must be planar across the whole area we've taken measurements. And then finally we can project that plane in space and determine its location. So if it's a contact between the dark and the light in this example, we can project where it is, and if we needed to excavate down to get onto the more competent layer or to remove a less competent layer, then we would understand the volume we're dealing with. And that's the engineering link. If we wanted to create a tunnel through here or any infrastructure, we want to know where those different rock types exist in space so that we can make our excavation, we can do our road cut, our foundation, whatever it may be, and anchor our infrastructure into competent rock. So that's how we can use our geological knowledge and the three-point problem to help us project in space where our layer may exist, and we can use that knowledge in our engineering infrastructure design.
Okay, everybody, coast is clear.